Now I am going to come to an important problem called a mixture of Gaussians. Okay. So first I talked about a single variable Gaussian, height for example. Then I talked about a bivariate or a two variable Gaussian where I had two measurements, height and weight, or three measurements, height, weight and chest size, right, and so on. And then we said the same way we can deal for a pattern classification problem, which is we decide which is more likely to have generated which distribution, and based on that we make a pattern classification problem. Now I am going to go revisit a problem which is the estimation that we talked about, right. So if you look at previously historically, how did we measure the means and the variances? So we fitted a curve and given the measurements we asked which is more likely, which mean and which variance for the one dimensional case is most likely to have generated those measurements, right. So this is the way we fitted the curve, okay. But now, and we did that by taking the log, just so that the multiplications become a summation, and then we took the derivative with respect to those variables and set it to 0, because we know that at every these minima, maxima, saddle points, they are always going to be set to 0. So their slope will become 0, right. Now I am going to talk about a more difficult modeling problem, okay, and I will explain what that modeling problem, that's the idea of a mixture of Gaussians. Here I am going to have a mixture of two population, but I do not know which population generated that particular measurement, okay, and therefore when I am trying to model it, it becomes very difficult, and I will explain the concept of mixture of Gaussians. This is very important. Once we do the mixture of Gaussians, the idea of hidden part of the hidden Markov model will also sort of become understandable, okay. Okay. So let me just take measurements. It so happens I went to a park, okay. So there is a park with parents and children, okay. I measured the heights, okay, only one dimensional now. We will go back to the one dimensional, no weights, no chest size, nothing. We only talk about heights, okay. Now what will happen is there are two distinct sets of population. One is the adults, right, which is the male and the females, and the other are children, okay. Because we are talking about in park, most probably these children will be less than 7, 8 years, right. I mean after 8 or 9, 10, after 10 years, of course, children become more mature, they stay at home. Nowadays, most probably, don't even come out, right? They are more busy with their mobiles and so on, right? So, but less than, let's say, 5, 6 years, most children who come to the park are small, right? So, I am only measuring the heights, right? So, what will happen? And I don't know whether it's a child or a male or a female. That information is not present for me, okay? So, now, if I look at the histogram, right, so I went to a park, I measured the heights of all the humans that are present there, okay. I found out at 2 feet 4 inches there were 25 people, 2 feet 5 inches there were 44, 2 feet 6 and 6 feet 1 inches 24. So, this is the measurement I got. Now, I can plot a histogram here, right. So, as usual, at 2 feet 4 inches, I count the number of people, at 2 feet 5 inches, I count the number of people, and I get a histogram like this, right. Now, of course, I can find out the probability. What is the probability in this population that the heights are between 5 feet 7 inches and 5 feet 8 inches? I will count the number of 5 feet 7 guys, 5 feet 8 guys and divide by the total number of people. What is the population that are between 2 feet 10 inches and 2 feet 11 inches? Again, I count, okay. But remember, I started my last class by the idea that I want to not carry this data as it is. Instead, I want nice closed form mathematical equations that describe this model. That's what we mean by a model, right? We are fitting a mathematical model to this data, right? And one of the typical models that we have learned till now is what? The Gaussian, right? The Gaussian is made up of two parameters, right? This is a single variable, right? There's only one height. So, we will try to find the mean and the variance of the Gaussian, right? So, if I do the mean and the variance, I will get something like this, right? Now, is this Gaussian described the data properly? No, right? It is showing me that mean is around 3 feet 6 inches. What does the what does the Gaussian capture? It says on an average which height has the most number of people, right? Here it is claiming that it's 3 feet 6 inches that have the most height. Why did this come? Because remember, in a maximum likelihood estimation, we are only taking the average value, right, which means we take all the height measurements, right, and divide by the number of people, right. That's what we are doing, right. So therefore, because this is like a two mode distribution, there are two peaks, right, two different peaks, the average is coming out somewhere in the middle, right, which actually where the least number of people are there actually, right. So we know that this is not a good model at all, right. Why is it not a good model? Because actually, when we are saying it's Gaussian, we assume that the model is following almost the Gaussian normal kind of bell curve, and therefore we are fitting a Gaussian. But here there are two different populations. There is a children population and an adult population which have very different characteristics. So a Gaussian, a single Gaussian is not a good model for this. Okay. So what can you do? You can say, okay, single Gaussian, this is not a single mode, it is no one peak, there are two peaks. So maybe what's the natural thing to do? Let us have two distributions, two Gaussians, right. So I fit a two Gaussian model for this. So instead of a single Gaussian, let me take two Gaussians, where one Gaussian will have the mean here and another Gaussian will have a mean here. Okay. So this is the model that I will go with. Okay. Therefore, I am going to say that my model now is a mixture or consists of two Gaussians. One Gaussian which will have some mean, let us assume for the time being that the variance is one fixed quantity both from the children and male. It can be adults also. Okay. So this is now the mixture of Gaussians. So now I am taking a mixture of two Gaussians, okay, and we see that this fits the data better than a single Gaussian, right, because a single Gaussian is going to look like this, and that is not a good idea at all, right. So sorry, did I make a mistake here? Yeah, sorry. So the single Gaussian is not a good fit, but generally a two Gaussian is a better fit for this kind of data, right. So therefore, we are going to say, I mean, we are seeing picture, I mean, visually seeing this, therefore, I as a human I am able to decide that this is a better model than this, okay. So that is a given, right. Now remember this, I am only given the height measurements, right, and from that I am fitting a two, I have decided because they seem to be two classes visually, therefore I should have two Gaussians. So what are the parameters of the Gaussians? Now because there are two Gaussians, each Gaussian will have its mean and its variance, and we assume the variance is same. Let us say the mean from the adult population or male population, its variance, and something called the coefficient of the linear combination or the weights of the mixture, that is what we normally call it, right. So we are taking a linear combination of two Gaussians with different mean and variance, and this becomes the actual model that fits this data, okay. So ultimately this is the density function. So remember, what should happen to this density function? If it is a, we are talking about probabilities here. So the area of this density function should turn out to be 1. That means if I integrate this entire thing, including this curve and this curve, the total area should be equal to 1, which is why there is a constraint on this weight. This pi 1 plus pi 2 should always be equal to 1, okay. That you can see in the extreme case, if one of the data is not there, the other data should actually come out to be only a single Gaussian, right. Remember here this n has 1 by root 2 pi sigma, all that is there. On top of that, there is an additional scalar which is telling the weights of how much, what proportion belongs to this Gaussian and what proportion belongs to this Gaussian. So the total obviously have to add up to 1. So this pi 1 and pi 2 are the proportion belonging to this child and proportion belonging to the male or adult class, okay. Now if I am trying to fit a two mixture model, now it is not bivariate, okay, it is a two mixture model. The measurement is only height, so it is a single variate, the variable is single, it is still a height, but I am using a mixture of two Gaussians and I have to estimate the parameters of the two Gaussians, right, which are the means, the variance or the standard deviation, and for each one of them and the corresponding proportion which I should get, how much weight should I give to this Gaussian. So, if I have a 2 mixture, there are 3 parameters: weight, mean and standard deviation as the first guy, weight, mean and standard. Actually, the second weight is not important because it will be 1 minus the other guy. Okay, so one less quantity that is there, but generally you can say 6 parameters I have to estimate. How do I estimate these parameters? We are going to do the likelihood. So, we are going to take these 1000 measurements, fit the probability, because these are independent measurements. The product of these with the variables unknown are the mu1, mu2, sigma1, sigma2, weight w1, w2, right, or c1, c2 or pi1, pi2, whatever. Different people use different notation. So, these 6 parameters have to be estimated that maximize the likelihood of observing the total data, all this 1000 measurements. Okay. So, therefore, that is the basic problem we are going to solve, but there is an issue here, right. When I measured, I did not know whether it is a child or a man or an adult. I mean, let us say adult and children. There are actually 2 categories, but you are going to give me only these measurements without telling me anything about the category or the class to which it belongs, right. So, I have no clue about what these classes are. Okay. Now, I can make the problem a little easier. How can I make the problem a little easier? If I also had an idea if each of these measurements belong to a child or an adult, then does my problem become easier? Yes. How will it become easier? Now, I will take, if I also had the category information, I will, like the previous case, I will take all the children. From the children, I can find the mean and the variance for that PDF. I will take all the adults if I have that information, fit likelihood for that, get the mean and the variance, and that will be the mean for the adults, variance for the adults. And how do I get the weights? I count the total number of children out of the population, and so that will become the proportion of children. So, if I had a category information, this becomes a very trivial problem, right? Because from the category I can easily find out all the children mean, the children weight, children weight proportion and the children variance, the adult population ka proportion, the adult mean and adult variance. But in many cases, we do not have that information. Somebody has forgotten to measure, right? So, there could be children, there could be adults, we do not know. And all that we have is only a set of measurements. Okay? And there are many practical problems that we will encounter in practice where such information is missing. Now, given that the information is missing, how do I estimate these parameters? That is the problem of the mixture of Gaussians thing. Okay. So, the issue here is that I have height and height measurements from a mixed population, from children and adult. Therefore, I know that it is better to have 2 Gaussians, but I do not have the information of which height belongs to the adult, which height belongs to the children. Okay. As humans we will say, hey, 2 feet 3 inches, I can guess it is a child and all that. And if it's 6 feet, I know it should be an adult. Okay. But there are, this is like our acquired knowledge. So, we should not think of it like that. In general, there could be some scenarios where I will not have any idea whether it's a child or based on the measurement. So, in general, we are addressing such kind of scenarios. Based on the measurement, there is no way that I can decide whether it's a child or a man, okay, or an adult. So, that is the more general problem, difficult problem that we will try to solve. So, we have a mixture of data which could come from 2 populations, but we have no clue which one belongs to which population. So, therefore, we have this problem of what is called unsupervised. Remember, if I had known the category, that is like supervised data, I know exactly where it belongs to. But here it becomes unsupervised. I have no clue which measurement belongs to which class, right? I have some clue that there are 2 classes belonging, and some, more often than not, we do not even know how many classes are there. It could be adults, children, female, male, or it could be boys, girls, children, male. Maybe all these could be, creating multiple, Gaussians. Okay. So, So we have no labels. That is the problem in a mixture of Gaussians when you are trying to fit a model for the data which has multiple categories in it. Okay. So again, if I had the class information and let's say now it's a 3 Gaussian, I have adults, children, males and females. So I have x1 is coming from a child, x2 is coming from a male, x3 from a child, x4 from a female, x5 from a female, x6 from a male. If I have this category information, as I said, problem is very easy. What will be the mean for the children? So now I'll have 3 Gaussians, and so therefore 3 Gaussians means 3 means, 3 variances or standard deviation and 3 weights. For children, obviously what will I do for the means? I'll take all the measurements that belong to the all the measurement that belong to children. So x1 belongs to child, x3 belongs to child, x8 belongs to child, x12. So mean is very simple. x1 plus x3 plus x8 plus x12 by the by 4, right? Because there are only 4 classes. 4 guys will belong to child, right? Similarly, if I want to do male, x2 plus x6 plus x9 divided by 3. Sorry, again I keep touching the monitor. Okay, and similarly female. So if I have the category information, that becomes very easy, and that is a trivial problem to solve, right? And we can easily estimate these parameters. But in practice, like I keep saying, I have only the height measurement. Somebody has forgotten to even find out whether it's a child measurement, female measurement or male measurement. Okay, and therefore that becomes an unsupervised problem. And what do we do, right? So what we do is called, it's actually a very strong mathematical idea. It's called expectation maximization, but we are not going to go we are not going to go into the math of that. The way I'm going to decide is that I'll arbitrarily assume some mean, some variance and some uh, uh, weight. Okay, so I'm going to assume, let's say, a 3 Gaussian model. Okay, a mixture of 3 Gaussians, something like this. But I have no clue. So how many parameters are there? There are 3 means, 3 variances, and 3 things. I don't have any clue. Okay, so I'm going to randomly put some values. Okay, so if I put randomly some values, this can be better understood when we talk about vector quantization. I'll come back to it. Then I am going to ask now whether a height measurement I got, is it more likely to have come from the first Gaussian or more likely to have come from the second Gaussian or more likely to have come from the third Gaussian. So because once I have randomly initialized, I have the value of all of these parameters, correct? And therefore, given a height measurement, now it's like a pattern classification problem. Now I know all of these 3 Gaussians. Now I'm asking, given the height, does it belong to this guy? Is it more likely this guy generated, this guy generated, or this guy generated? So once I know that, I'm going to assign that height now a value. I'll call it child. A next measurement comes, I find that it's more highly likely to have come from male. Third measurement comes from female. So once I have this random weights, right, randomly initialized, then I get some idea like this based on a classification kind of idea. Now with this things, I update my mean variance for the children class, for the male class and the female class. So then these 3 become updated values. Once I update, now again these values get fixed. Then again I go back to the same measurements. Now with this new updated means variances of this mixture of Gaussians, again I take the original measurement, ask is it more likely. Now because things have changed, which was more likely, the category can change to another class, right? Now again I'll update all of those measurements and I'll get an updated assignment of each measurement. Each measurement, this can change again. So the same measurement with we might get assigned to another class. So again I get assignment So once I get this assignment, again I update, right? So it's an iterative process. So I'll keep doing it again and again and again until the values of the mean, the variance and all don't change, which will not change if the category assignment does not change, right? After I fix, it keeps on giving me the same, the first measurement is always get assigned to the N1, the first Gaussian, the second measurement always gets assigned to the third Gaussian, the third measurement always get assigned to a second. Once the assignments do not change, then the parameters are not going to update, right? I mean, they're going to remain fixed. There's no change that's going to happen. So again, you will get the measurements not changing. So we keep repeating it, but in practice, we stop after some n number of iterations, okay? Or when the likelihood, we will talk about that a little later. So this is also a likelihood estimation. This is an iterative approach to estimating the likelihood across the entire 9 parameters, okay? So this is what is basically called an expectation maximization algorithm, and the reason why it has to do this iterative method is it has no clue or there's hidden information that which category belongs, which measurement belongs to which category. So there is this hidden part which is also sometimes called latent information, which is not available, and you try to predict with some initial guess, try to get the class assignment or which the latently which or hidden part, where does it belong to. With that, we again update the parameters, again we try to find out a better fit of the data to the estimates, and we keep retain. So this is what we call as an iterative algorithm, and in this case I'm doing something called hard allocation. So I'm not going to go into the details, but this is a basic idea of a mixture of Gaussians, okay? So I will stop this, and next class we will talk more about hidden Markov models and so on, right? And continue from there. Okay, thank you.